Hello, and welcome to the third and final lecture on solar cells. In this first section, we'll talk about the physical structure of the material. There are three general structures of materials. If there is no order, generally speaking, the more crystalline a material is, the better a solar panel it will. Crystal structures are made up of two general components, a basis and a lattice. The basis is a simple pattern of atoms that is repeated at every lattice point. A lattice is just a repeating 3D structure of points. In order to describe a lattice, we break it down into a unit cell. A unit cell is a cube containing lattice points that, when repeated, constructs the lattice. A simple example is a simple cubic structure, where each corner of the cube is a lattice point. In the example on the screen, the basis is a single atom. An important thing to note is that in this structure there is only a total of one atom, as only 1/8 of each of the atoms at the corner is in the unit cell. Another example is the face-centered cubic, or FCC structure. It is like the simple cubic structure, except it has an additional atom in the center of each face of the cube. One important lattice structure is a diamond lattice. It gets its name from the fact that it is the structure carbon atoms make in a diamond. This structure is also the structure of silicon and some other solar cell materials. As you may have noticed, it is similar to the FCC structure, as if you just look at the atoms highlighted in red, it is the FCC structure. The addition of the blue highlighted atoms are what makes it a diamond unit cell. The diamond structure is in fact an FCC lattice. However, the basis consists of two atoms instead of just one. If you put a bunch of these together, each red atom at the FCC lattice points has a blue atom bonded to it, as shown. Materials are rarely perfect, and often have some defects. Defects at a specific point in the lattice are called point defects. There are several types of point defects, and they are as follows. A vacancy, where an atom is missing from the crystal structure. An interstitial, where an atom is in a space that is not part of the crystal structure. Substitutional defects are when an atom in the crystal structure is replaced with an atom of a different element. And lastly, a Frankel pair is when an atom in the correct place moves to an interstitial space, creating a pair of interstitial and vacancy defects. Line defects are where unit cells do not line up properly. There are two types. An edge dislocation is where the faces of two unit cells meet up with the face of one unit cell. A screw dislocation is where the corners of two unit cells line up diagonally instead of straight. Lastly, at the surface of a material and at the boundaries between different grains, there are major disruptions to the crystal structure. These defects are simply known as surface imperfections. In this section of the lecture, I'll be talking about some of the more complicated aspects of how solar cells work. Recombination is when an electron at the conduction band drops back down to the valence band and releases energy before it can be collected in a useful manner. There are three different types of recombination. The most basic type of recombination is radiative, and this is more or less the opposite of absorption. An electron at the conduction band drops down and fills a hole at the valence band, and the energy is released as light, or a photon. This is how LEDs work. Defects play a role in the single-level trap recombination by creating a stable energy level between the conduction and valence bands. This band is called the mid-gap trap. An electron from the conduction band and a hole from the valence band meet at the trap, where the electron fills the hole. The trap makes recombination easier by reducing the jump in energy required for the electron to meet the hole. Energy is given off as heat. The last form of recombination, although spelled like auger, is pronounced Auger recombination. Similar to radiative recombination, the electron drops down and fills the hole. However, instead of being released as light, the energy is transferred to either an electron at the conduction band or a hole at the valence band. This causes them to jump in energy similarly to absorption when the photon energy is greater than the band gap. Since this is not a stable state, the electron or hole will drop down to the closest stable band, and the energy is released as heat. One thing I mentioned in the last lecture is that holes can move similarly to free electrons. This happens when a nearby electron bonded in the valence bond moves to fill the hole, which leaves behind a new hole where the electron used to be. So while holes are not a physical thing that moves by itself, its movement behaves very similarly to that of free electrons. Substitutional defects are sometimes intentionally induced in order to alter the properties of the material. This is called doping. In solar cells, doping is used to create p-type and n-type materials. Again, silicon will be used as an example here. N-type silicon has phosphorus substituted into the lattice. Phosphorus has one more valence electron than silicon, so once all of the covalent bonds are formed, a free electron is left over. Overall, N-type doping adds free electrons to a material. P-type silicon has boron substituted in. Boron has one less valence electron than silicon. When it forms covalent bonds with the surrounding silicon, one of those bonds will be missing an electron, which creates a hole. Overall, P-type doping adds holes to a material. For silicon, phosphorus and boron are the most common doping agents because they have a similar size to the silicon atom, which allows them to fit into a lattice. If you are to make a solar cell simply out of pure silicon, it would not generate any power. This is because all the energized electrons will travel in random directions and cancel each other out. In order to generate electrical power, we need to have all the charged electrons to travel in one direction. This is achieved by creating a p-n junction. A silicon solar cell is made up by a thin N-type piece of silicon on top of a thicker p-type piece of silicon. The interface between the two is called a p-n junction. When these two slabs of silicon meet, diffusion begins to occur. The holes in the p-type will want to go from the hole-rich p-type region to where there are not many holes, the n-type region. They will travel a certain average length before filled by one of the free electrons in the n-type region. Vice versa for the free electrons in the n-type silicon. The combined area where the electrons or holes travel into the other material is called the depletion region. If diffusion was the only thing happening here, eventually all the electrons or holes will combine, but that is not the case. Let us take a look back at doping. In the n-type silicon, when the free electron moves away from the phosphorus, a negative charge is leaving a neutral atom and leaves a positively charged phosphorus atom, which is engraved in the lattice and cannot move. Same story for the p-type silicon. When the positively charged hole moves away from the neutral boron, it becomes negatively charged atom embedded in the lattice. Therefore, as diffusion occurs, a fixed positive charge grows on the n-type side of the depletion region, and a fixed negative charge builds up on the p-type side of the depletion region. This fights against diffusion, as the growing positive charge on the n-type side will begin to repel the holes from the p-type side, and the growing negative charge on the p-type side will begin to repel the free electrons from the n-type side. Eventually, the push of diffusion and the force of the growing electric field reach an equilibrium, and diffusion stops. Now, when exposed to light, the energized electrons generated will be attracted to the positive n-type region at the top of the solar cell. This causes all of the energized electrons to flow to the top of the solar cell, and with them all traveling in one direction, electrical power is generated. This concludes my lectures on solar cells. Thank you all for watching, and I hope you learned something.